Recording in progress.
Time to start, Zuhail.
Okay. Well, thank you, Olga, for asking me for this very pleasant duty to introduce two very distinguished scientists for plenary speakers this morning here in College Station. Our first speaker is going to be Suzanne Yellen, who has made many distinguished contributions in the field of quantum coherence, nonlinear optics, ultra-cold molecules, and superradiance, and many other fields. Presently, she is a professor of physics at Harvard University, and she is the director of this Harvard Center for Ultra-Cold Atoms. Suzanne received her diploma from the University of Stuttgart in 1994, and then completed her doctorate from Ludwig Maximilian University in Munich, while also being a research student at Texas A&M University, where I first met her. But then after her PhD, she did some postdoctoral work at Hanscom Air Force Base, MIT, and ITEMP at Harvard. In 2002, she joined the University of Connecticut faculty, and then joined Harvard University as a professor of physics in 2010. Suzanne has received many honors. Here I mention just one because of time limitations, and that is the Willis Lamb Award for Laser Science and Quantum Optics in 2013. This was given for her pioneering contributions to the theory of coherence phenomena, ranging from superradiance to ultra-cold molecules, a very wide range indeed. So, Suzanne, I invite you to give your talk, which will be on this very exciting new area, analog quantum machine learning. Suzanne.
Okay. All right, thank you. So can you actually see my screen, because I don't see you anymore now?
Okay. Yes, at least I can, but I'm sure
Okay.
everybody else can.
Excellent. Thank you so much for inviting me here, and good morning. It is not quite as early as in Texas, but it is definitely morning, but good afternoon to everybody in Europe and so on. So we have started to work on quantum machine learning when COVID hit. That was just a good time to try out something new, because everybody was sitting at home and trying for new things to do. And in the meantime, there's actually quite a bit of overlap also with the quantum optics work. And I will just give you a little bit of an overview. I will not have too many details. I'm sorry. Please do interrupt me with questions at any time. I'm perfectly happy to cut pieces out, etc., or borrow from my question time at the end of the talk. Okay, so this is about analog quantum machine learning, and the analog has two reasons. The one is because I find that totally fascinating and very promising, but the second is that this is also really the best way to use present-day hardware. So to take a step back, the step from machine learning and quantum computing to quantum machine learning is actually kind of logically a very obvious one, and the quantum machine learning community by now is actually pretty big, and we could and can also see some of that at this LPHYS. And the big question at the end, of course, is whether machine learning on a quantum computer can actually speed up the process compared to the classical machine learning and AI that we know. And as you all know, there are not really huge, fast, reliable quantum computers yet. And so this is actually something which is relatively hard to test. And so one of the questions is, how far can we go in kind of really understanding what the possible advantages are with the limited means that we have so far? And this you have to take a little bit as a background for my talk. So analog computing is also basically neuromorphic computing. So neuromorphic means brain-like. And here is a little depiction of how we can imagine the neurons in the brain. These are these little red dots are the neurons, and the black lines are the axons, the connections between those. And as we very well know, the brain is resilient to noise and disorder. It does the computation in an analog manner and has obviously evolved to excel at learning tasks. And if we now look at some near-term quantum technology, and here I've written the NIST, the Noisy Intermediate Scale, but I'm in particular referring, and I will also explain that later, to these Rydberg atom arrays that are that have been pioneered here at Harvard and are sprouting everywhere in the world. This typically consists of few hundred, or in the meantime, actually a few thousand qubits. Obviously, all the operations are decoherence limited, but they are, as far as everybody knows, so far there's no limit to scalability. And of course, all the experiments are moving towards full control, but that's not there yet. And what I'm going to talk about assumes kind of limited control. So the idea behind quantum algorithms inspired by the brain is to reveal the analog computational power of those devices, aim to deliver potentially scalable quantum machine learning algorithms, and of course also understand the physics behind the possible quantum advantage. So before I start, I would like to introduce some terminology. So you all know what neural networks is, and then there is this neuromorphic computing. That's the name for brain-like architecture for computational network. Then there is the next kind of, in the hierarchy, is the so-called recurrent neural networks. So most of the machine learning and deep learning, etc., that you read about in the newspaper or so, is a purely feed-forward network. So it goes through all the layers step by step. Recurrent neural networks, on the other hand, they can also have cyclic connections. So it's more like the brain, it moves through this whole thing any which way. And then the next part of the hierarchy is the so-called reservoir computing. This is a special case of this recurrent neural networks, and I will say a little bit more about that in a second. Please do note that these are all definitions for classical neural networks, but of course the analogs for that in quantum all exist, and I will go through them step by step. So let me talk a little bit about reservoir computing. So what you see here is a recurrent neural network. There are some nodes which we call spins. This is why all the nodes have S. I've denoted them in blue and red for either firing or not firing, or either being on or off. A few of those serve as inputs, and you can, for example, kind of just send some kind of functions into these input nodes. And then there are output nodes, which you just take a few. And these output nodes are then with some kind of function, which is usually a linear kind of function, W out, into the solution Y. And in addition, we have these connections, J and M. These are just the connections between node M, or spin N and spin M. So typically neural networks have trainable connections, J and M, and these output filters, W out. However, in a practical, physical sense, training these JNNs, these connections between any neuron and any other is very resource intensive. So that's why people came up with the idea of reservoir computers, where you say, okay, you have some connections between some N and M. They have a fixed connection strength, J, or they have no connections. And you cannot change this over the course of the learning. And obviously, that kind of limits what you can do with that, but it's a lot less resource intensive. And it turns out that this is, in the classical world, for kind of some learning tasks, actually extremely effective. And then again, this Y is the solution that we are looking at the end. So how do we train such a network? So there is this so-called update rule. The update rule that means every spin gets updated during the training dependent on A, spin-spin interaction, and B, interactions with the environment. So you send the input in, then it develops a little bit, and then you can read the output out at the end. Mathematically, that would look, for example, like this. Every spin N has a kind of what you can call a local field, H, which consists of these connections or synaptic weights, to use the brain-like brain structure language, and an environment stimulus that comes in there as a bias. And then this evolution is just very simply, if this local field is larger than 0, or for example, larger than 0, then we don't change the spin. And if it's smaller than 0, we flip it. That's all. So a typical training cycle then looks like that. The goal of that is to optimize a set of parameters, for example, all the JNNs and this W, to give the desired output. So we train that a couple of times and then compare with the training data and see whether it comes out right. So that consists of 2 steps. The first is the update. That's what I just told you. This is, you put some input, you let the machine evolve, and then you take the result that you get and calculate the loss function. So this loss function, for example, is the overlap with the desired outcome with all the training data sets, and calculate a new set of parameters. And this is typically done, for example, via gradient descent. And then you send this new set of parameters back into your machine, and you start this process all over. So this is how classical recurrent neural networks, for example, work. So now we quantize this. Now our spins are quantum spins, for example, 2-level systems, as I've shown here. Basically, the rest is pretty much the same. And now we have basically the same field local field that we had before. This small hn is the same. But we packed that one into a total all-over Hamiltonian, as one is wont to do in quantum, where one has this local update rule, which is the same as in classical, plus a sigma x term with a driving term that facilitates the flips of the quanta, because this flip cannot be done like in quantum where we just say, okay, you either do it or not. Your Hamiltonian is there, and the whole system will evolve according to the Hamiltonian. And then, in order to get basically the same thing as before, flipping means that omega times the time we let this evolve is pi. And here we can see from the way how this Hamiltonian looks like, if this local field is much stronger than the driving field, then the spin doesn't flip. And if it's much smaller than the driving field, it flips. So in principle, we have the same thing in quantum that we had before in classical. And there's, of course, quite a couple of things, a couple of people who have done this before, with a couple of detection applications like entanglement detection, time series prediction, long-term memory, all of the kind of things that you would typically want to do with a brain-like architecture. The thing is that they all assume large-scale universal quantum computation, Whereas what we want to do is, as I say, analog or analog digital hybrid near-term devices. And so this is what I'm going to talk about from now on. And here, this learning training cycle for the quantum reservoir computer is the same as for the classical. We do this update that I just explained to you. And here one has to understand that this is still always run as a hybrid, where this right kind of optimizing circle is typically done classically. And I will briefly come back to that later. Because this calculating a loss function is fine, but this kind of something like gradient descent or so, a quantum computer is not very good. Okay, so so we can do basically the same thing that the quantum that the classical can, but the question is, can we also do something more? So here is again this update rule for every kind of individual spin. And what are now the quantum features that we could potentially take advantage of in addition to what one had before? So the first is that one, of course, has interference and the freedom of the choice of measurement basis. And this can actually be used for error detection. I'll show you an example of that in a second. The second is that these arbitrary measurement bases can produce training speedups relative to classical recurrent neural networks. And of course, because this is quantum, anything where we need stochastic processes, which actually for all of this kind of learning, brain-like learning is often very important and kind of naturally works better. So let's just have a very brief look at this arbitrary measurement basis, what I mean by that. So here's the same slide that I showed before, where we have this update rule, where the spin flipping would be omega times the evolution time is pi. But of course, nobody says that we have to stick with pi. We can here use any rotation angle, and this, of course, kind of gives us a whole new kind of dimension of learning that we don't have before. I would like to also show you one kind of implementation, which is very simple, where we can use something like that, which is, for example, make a parity computer. So we have two spins, and we try to figure out the parity of those spins. And the way this is done, we have our two spins, sigma 1 and sigma 2, and one extra spin in between. So now, and these are connected via this element J. And so this output, so this middle spin is the output spin, and this local field on the output here is given by J times the sum of these two other spins. Obviously, this term is only non-zero when if these two spins are the same, either both +1 or both -1. In that case, we switch the Rabi frequency such that that nothing happens. And so what we get is at most a little bit of a wiggling around the original -1, or whatever our original value was. On the other hand, if our two spins are different, then this H output is obviously 0. And so the Rabi frequency is much stronger, and this flipping actually happens. So this is this would be basically one of the essential steps that then can be, for example, also later be used for error correction, etc. So I would like to take a minute or so to explain this Rydberg arrays. I'm sure you have all heard about that. So I give it one slide. So this is an array of atoms which have their excited state in the Rydberg state. And for example, here this is rubidium, where the Rydberg state is a 70 n equals 70 state. And if we are in that state, we obviously have a van der Waals interaction. Which if the kind of if two atoms are far enough apart, that is not really visible. But if you bring them closer and closer, there is this van der Waals interaction which changes the effective kind of level of this upper state R, such that the usual driving field that we had before is not in resonance with the upper state anymore. So that means we can excite one, but not two atoms within a certain radius. And this is what is called Rydberg blockade. This has been around since the early 2000s. And this is at the basis of this so-called programmable Rydberg arrays, which uses optical tweezers. And here is just a picture that I stole from the kind of Lukin, Greiner, Vuletic groups here, where they show that they can use this effect, for example, to do antiferromagnetic. What I want you to look at is this equation on the right, which shows the native Hamiltonian of these arrays. And if we look at that, we get exactly these three terms that we have. The first term is this kind of local kind of bias term. The second one is the interaction term, basically this J and M. And the third one is this kind of Rabi frequency flipping term. And I would also like to emphasize at this point that what we can do here is actually goes a little bit beyond just having completely constant J's. But in principle, this is a kind of an on or off proposition. So we are really at this quantum reservoir computing architecture. Okay, so there are a couple of examples. One is quantum error detection, which basically is based on this kind of interference idea or kind of parity check idea that I just showed you. One more is multitasking. That is something which is kind of seen as a typical brain-like thing. And here are the results from some kind of simulations that we did. These three truth tables are for an XOR, an AND, and an OR. Sorry, XOR, OR, and AND. And we can see that the fidelity, even for, I think that was run on a simulated reservoir computer with I think 6 qubits. So that's actually already pretty good. And the last one is memory. And I will not show this memory solution here. And now I have to kind of find where I am. But what I would like to show you instead is an example where we actually have tried to benchmark a typical classical learning task, namely how to recognize handwriting. This is this so-called MNIST. Everybody who has ever done any kind of machine learning of any time has seen this. There are a lot of training data available, so this is an easy way to do this. And here, what is shown is a table where our procedure tries to kind of recognize these digits that are shown on the left. And what is done is we train 10,000 samples and test 1,000 samples, and what you see is just a kind of 36 of those 1,000. And on the right is the solution. And we also compare that with classical method. And here you see there is the first, the second, and the fifth are classical methods, which use kind of more than 200 neurons and use nearly 20,000 tuning parameters. Our method is a Rydberg array, which is here already much bigger than what I showed you before, namely a Rydberg array with 15 atoms. That's if you use the right computation and numerical methods, etc., you can do this. You can do up to 15, but this is actually a serious kind of calculation already. And as you can see, this orange bar that we see here. It does as well or better than these classical methods. But it can be readily implemented, and in fact, that's one of the things that they are at Quera here. What they are doing at the moment, they are training these things on the actual hardware. So one small step in between. I talked already a lot of quantum classical hybrid, and for the foreseeable future, we will need that. So we might as well make the best of it. So here is our quantum machine, and I already told you that we do this gradient descent or whatever classically. But now let's try to get one step further, and let's make even part of the circuit classical. So we call that a virtual circuit. And as an example, we take a Clifford circuit. A Clifford circuit is, and I don't need to go into detail, but a Clifford circuit is in principle a quantum circuit, but one that is actually efficiently classically simulable. And there are a couple of other of those circuits. They cannot do as much as the full kind of spectrum of quantum circuits, but they can already do a lot more than just typically a classical computer. So we take the limited tunability, high expressibility, and of the quantum analog machine on the left side, which, however, has evolution that is limited by decoherence, and combine it with the easily runnable, tunable, non-decoherence limited virtual circuit, which, however, is not quite as expressible. But together, we basically have the best of all worlds, and the trick is now basically how to best distribute our calculations on these two parts. And combining these two approaches promises both the enhanced expressivity and trainability, but nevertheless, we use it on a near-term device. And we use this approach just to benchmark another system, namely the quantum chemistry of water. And that's, of course, trivial. Everybody knows how water looks like, right? And here I just show you an example where we compare the classical calculation, which is the LPHYS'23, with the quantum calculation. And the K that you see here is basically how many actual real quantum elements do we put in here. So as you can see here, this is between 0, where we use only the virtual circuit, which is already much better than the LPHYS'23, and then kind of make it more and more quantum. So that actually works pretty well. For the remaining like 6 or so minutes, I would like you to take you a little bit deeper into this idea of this quantum recurrent neural networks. So I've shown you a couple of examples that in principle they work, but I showed you nothing, and because the reason is because nobody knows why and when do they actually work very well and when not. So the question is, how can one prove a quantum advantage? And once we know this, can we actually build optimal quantum algorithms systematically? So the easiest, or for us most obvious question to ask here, let's take that apart into its smallest building blocks, like for universal quantum computer, this kind of set of single and 2 qubit gates. For analog computers, that's not as obvious. But there were some kind of people who had smart ideas before already, who kind of took a artificial neural network apart in the following way. You have a number of input qubits, these are the ones in blue, and one output qubits. This is a classical idea, and these were called perceptrons. And the perceptron alone, classically, is of very limited use, but altogether they obviously make this full artificial neural network computing. So I showed here a couple of these perceptrons put together. The thing is that each of these output functions gets an activation function. That's the one that you see on the lower right here, which is basically, for example, sigmoid function or something like that. Which makes sure that this architecture is resilient to noise. So if you look at these two kind of blue lines, you see that even though this kind of local environment is quite a bit different for these two, both of them would make our neuron be on. And now the question is, of course, can we do something like that for quantum? So here is the perceptron in a little bit more detail. So we have again this output qubit with this, which is this local environment, which it takes from all the input qubits. And then we put the solution of the output qubits through the sigmoid function and give the output. That's the classical version. The quantum version basically works exactly the same, except that, of course, we don't have this nonlinear function there. We have only unitary, and the only thing that we have is basically this driving omega times sigma x. So we have the inputs creates an effective force on the output qubits, and then we have this kind of driving field that rotates the output qubit, and then we get some kind of function that, however, doesn't look like on the left side. So the question is, how do we get from this kind of typical unitary function to this kind of classical type activation function? And this can actually be done if we allow some X and Z directed pulses to the time evolution. And I'm not going to show how this is done in detail, but we have actually calculated some, so that works very well. The second question is, if we want to look at the perceptron alone, how can we implement that? Because in principle, this requires two different qubit types to start with, the output one and the input one, which could be, for example, done with different Rydberg state, or one uses two different species array, or even having reconfigurable architecture. And I should really say that these all do actually exist. And if we take this into account, we can show that a single quantum perceptron is actually universal. In order to be universal, one needs three elements, and I show them all first. One needs an entangling gates. We do have that, and I explain in a second. We need single qubit gates, and we also need the identity, which for an analog computer, unfortunately, is not that trivial. So the entangling gate is, if you drive this middle field is really, really strongly, then the input from these two outside blue qubits doesn't matter. So this basically gives effectively this kind of Hamiltonian part that we see in the lower part, which is obviously entangling. The single qubit is needs small pulses on the individual qubits. So that's something that in principle we need in addition. And the identity is basically just done by dynamical decoupling, and I'm not going deeper into this. So the upshot is that a quantum perceptron, it gives a step to a universal quantum computer, but we need single qubit pulse control. So what does that mean? Does that mean our quantum reservoir computer is a universal quantum computer? No, that's not. Yes, but this is not the best way to run that. That would be really kind of a ridiculous way to run this. But what it tells us is that this reservoir computer has the same full expressibility of a full quantum computer. So this is basically the first step that we needed to show that this is actually fully functional. So in order to do the next step is that the easiest is to actually formulate this quantum perceptron as a traditional quantum circuit, which I do here. This is actually just very briefly, this is the input is the red, the output is the green. The green, of course, you measure only on one line because we've only one output qubit. The input is all but this one. And this evolving consists of this Hamiltonian of the machine, this is this middle step, and the single qubit rotations that we have there. And everything else is done on the classical computer. So don't bother about the details. We have shown a couple of things that work very well, but I want to show you two particular examples because I'm officially out of time, so give me one more minute, which work very well. So I've shown you before that we basically, with a strong driving, can entangle the two neighboring qubits. In particular, if we look at the Hamiltonian just for these two blue and green qubits, we see that this input, the total Hamiltonian is the input times, of course, the output qubit, and this adds up in the following way. So the plus and the minus are the plus and minus superposition of the for the output qubit. So if we add to that single qubit rotations, but they are global single qubit rotations, so they are the same for every single of these input qubits. So that's something that actually can be run on the experiment in all three X, Y, and Z directions. Then the effective Hamiltonian that one can simulate with that looks like this. And here, please do note before this was only for the first term was with sigma z's, the second term was with sigma x's. Now we have the full freedom here, and that means that this input, this circuit kind of simplifies to what we had, what I showed you before. Compared to that, is actually much simpler. And if we now prepare our input qubits with whatever input state we want to measure, and the output states in the 0 or the ground state, and then measure the output qubit, then one can see that this measurement gives actually the energy expectation value of the Hamiltonian for this particular input state. So this is something which on a universal quantum computer is actually relatively hard to measure. So here, and this sounds a little bit like magic, it's actually just a Ramsey measurement. So if you kind of get down to it, it's very simple. But the upshot is that single qubit measurements, if we do them often enough, give us the energy of a many-body system. And just to go one step further, what else we can do with that? We use exactly the same Hamiltonian that I just showed you. And if we look a little bit further into that, then we see that we can, in principle, do a time reversal of the input Hamiltonian just by flipping the output spin from plus to minus. So what can we do with that? For example, we can use, we can do a metrology protocol that is actually done already in a very, very simplified way in, for example, Vladan Vuletich's lab. So we start with the output qubit in 0 and with whatever the input state that we have. We let it time evolve for time tau. And ideally, we choose the Hamiltonian here such that it squeezes or scrambles the input state very strongly. And therefore, the output qubit is not touched, but the input qubit has changed. So then we put the sensing operation on, and ideally, this psi t is now such that it has a very high quantum Fisher information. So this one would be really kind of have very complicated, for example, a very complicated Wigner function, so that if we sense whatever, for example, a gravitational redshift field or something like that, the change of this input is maximal. That, of course, is traditionally very hard to measure, but now we flip this output to a minus, and then we do again a time evolution for tau. But because this spin flipping means that we are now going backwards in time, if our sensing wouldn't do anything, we would basically come back to where we started for the input qubits. But since we have done this measurement, we come to a what I call a psi 0 prime. And the psi 0 prime now, in many cases, is very, very different, but is again in a measurement basis, for example, a kind of a, so that we actually really, that this difference between these two is measured, and this protocol amplifies the difference potentially considerably. And with that, I have some more, but I will stop at this point and just briefly thank my group and thank all the people who did their main work on this. And with that, with that, I'm actually done. Thank you so much.
Well, thank you very much, Suzanne, for such a wonderful talk. I mean, This is really a very novel area, neural networks being treated within the context of quantum optics. The talk is now open for discussion. Any questions, please? Okay, well, any question? Well, okay, so maybe then let me see, is there someone asking question?
Can you hear me now?
Yeah.
Quick question, or I don't know, maybe not so quick, but Susan, what is your prediction, analog versus digital?
You mean in quantum?
Run, or digital replace analog like it did in classical computing?
Well, sorry. I have to say, one of the reasons why I love this analog is that I actually think, let's say for the next, don't quote me on that, but for the next few decades, analog will give you a lot of useful stuff. Whereas with digital, let me actually show you one more, just to kind of show what I mean. So here is a paper. This is about here. Here is a paper. I think by the people at Microsoft, who kind of looked how digital computing, and forget about this quantum chemistry, etc. I just want to show this particular graph. They made an estimate. If you have a perfect universal quantum computer, you have the runtime in seconds, where they, I think, assume something like a millisecond for one operation, or perhaps actually a microsecond for one operation. The runtime in seconds on the x-axis versus the number of qubits in millions on the y-axis. And they see what the main tasks are: quantum dynamics with certain limitation, general quantum dynamics, factoring, this is the Shor's algorithm, and quantum chemistry. And the kind of these, the most useful are obviously somehow the blue and the red ones, and in particular the red one, because factoring is one application. Quantum chemistry is pretty important. So what you need for that is of the order of 10 millions of physical qubits and a time frame that goes somewhere from a year to a century. So this is kind of, this of course makes certain assumption, but that is what you could kind of expect for digital computing. If you do the same thing with analog, and we have actually a suggestion out on this with which runs on analog, which should come out on the archive in the next few days or at least weeks, where we do this for analog, where we basically can do a lot of these tasks already now. So finally, of course, hopefully we can do something universal where we don't have to think what is the architecture behind this. Useful in any of kind of the lifetimes of people who are on this call. I would say I would definitely always put all my money on analog, and I would actually put it on analog in a way that this is useful starting between now and very soon.
Okay.
Thank you.
Any other question, please? We have time for one question.
You said don't quote you, but
maybe
you know,
a short comment. I think it
YouTube
depends
forever.
on the problem, where to use analog, where to use digital. And I think Suzanne have shown to us that analog is extremely promising for treating of these neural networks, right?
Well, it sure, yes. It is basically a neural network. The point is, what I've shown you is really kind of getting back in a sense. Artificial intelligence is called neural networks, right? The original idea was to kind of mimic the brain, but they're simpler. That is classically, and actually also with the universal quantum computer. In any way, when you do it digitally, it's much easier to do that kind of in one direction only. But of course, the best quantum computers that we can build don't have a serial structure. They have this kind of, like, for example, these arrays, they which can be reordered, etc. So we might as well take advantage of everything that we can that already is kind of a priori mimics the brain architecture. And then we add a little bit of quantum to it.
Okay, well, I think the time is up. It's certainly a very, very interesting talk. I had some questions, but maybe sometimes later.
Well, thank you so much again.
So let's thank Suzanne. There is no opportunity to clap except for myself.
Thank you.
Okay, so let's move on to the next talk. And it is again my very great pleasure to introduce Girish Agarwal. Girish Agarwal, this is a particularly pleasant experience for me, because Girish and I have sort of a trajectory which crossed at many points, especially at the beginning and the present. We both got our PhD from University of Rochester, working for the same advisor, Emil Wolf. I joined my PhD in 1974, and I tell my students that even at that time, Girish was like a legend for us. I mean, we always heard that there was Girish Agarwal, who graduated a few years ago. So, and Girish Agarwal happens to be a university distinguished professor at Texas A&M right now. Both of us are on the same faculty, on the same floor, essentially. Girish had a very, very distinguished career. Indeed, it is very difficult to introduce him because he has worked on so many different problems. I mean, if I say he has worked essentially on all aspects of quantum optics, that would not be an exaggeration. He has received many honors. He has been perhaps the most distinguished honor is that he became a fellow of Royal Society in England, and he won the Max Born Prize of the Optical Society of America and Charles Townes Prize of Medal of the Optical Society, and very recently he won the Sharlow Prize of the American Physical Society. He won a TOS, Third World Academy Prize in Physics, and Humboldt Research Prize. I mean, the list really goes on. So I think I better stop here and request Girish to give his talk, which will again be on something quite novel. I mean, bringing ideas from another field to our quantum optics area on magnonics. So Girish, please.
Well, thanks, Suhail. So let me see how I share my screen. Yeah, you can see my screen?
Yes, of course.
Okay. So first of all, thanks to Olga, and I'm so happy that Olga and her colleagues continue to manage to organize these conferences on laser physics year after year. It's a wonderful experience to be at her conference. So I'm going to talk today about some of the quantum optics ideas and the applications into a very different field, that is the field of magnonics. I do realize that for most of you, the field of magnonics is very far away from what you do, but I'll try to give a broad overview and keep the discussion as simple as possible. So the work has been done with two graduate students, Mukhopadhyay and Nair, and postdocs Jay Lee and Jedong Jiang, and of course with colleagues Marlan Scully and Xiao Chu. So here is an outline of my talk. I'll start with some of the ideas from cavity QED and how these ideas have been implemented in the context of the interaction of magnons and photons, leading to what's called the polaritons. And actually, I got interested into this field after I saw the experiments on a strong coupling of magnons to the photons in the cavity setup. So then I'm going to tell you about the cavity-mediated interactions between the magnons, which can lead to both level attraction and the level repulsion. The internal fields in magnetic systems can result in the nonlinearities, which would then correspond to nonlinear polaritons when you couple the such magnons to the to photons, and which would result into the traditional nonlinear effects like the like the bistability and the multistability. Now, another area which is now moving very fast is the case what's called the the waveguide QED, and here we can dissipatively couple magnetic systems. This leads us to the realization of the anti-PT symmetry, which has sensing applications, and this also leads to what's called the bound states in continuum. I would show how the idea of the bound states in continuum can be used to enhance interconversion between the microwave and optical field. And finally, I would show how the ideas of the quantum state transfer can be used to prepare the quantized states of the macroscopic systems. So let me start by a very brief introduction. What is the magnetic system that we are looking at? We are looking at systems like the ytterbium garnet spheres, and basically these are the systems with very large number of spins. Just to give you an idea that if you have a YIG sphere of 1 millimeter diameter sphere, it would have total number of spins which is of the order of 10 to the power 18, and the individual spin here has a value 5/2. So that would be the total spin in a sample which would be of 1 millimeter diameter. So if the sphere is placed in a static magnetic field, then all these spins are aligned along the direction of the static magnetic field, and any perturbation is going to make these spins precess around the direction of the magnetic field. And in these spheres, there is a very prominent mode which is called the Kittel mode. And most of the things that I'm going to discuss is the coupling of the Kittel mode to the photon. So this is a especially uniform magnon mode in the long wavelength limit of the spin wave. Okay, so there is an exact transformation between the spin variables and the bosonic variables, and this is expressed here. This is known as the Holstein-Primakov transformation. And please note that for this system, the ground state is the one in which all the spins are up. And if we are talking of a excitation in the system, that means that we would turn one of these spins down. So this would be the excited state for this spin system. This is sort of opposite to what we are traditionally used to dealing in quantum optics, where the ground state is the one where all the spins are down. And that is the reason that the spin creation operator here is related to this bosonic annihilation operator MMI. So now we look at the coupling of these spins to the cavity field. So we have a coupling here, the magnetization of the spin system coupled to the magnetic field in the cavity, and the effective Hamiltonian can be written in this form. This is almost like the Jaynes-Cummings Hamiltonian of quantum optics, except that the role of S minus and S plus is reversed, and that's for the region I mentioned here. The ground state of the system is the one in which all these spins are up. So once we have this kind of a Hamiltonian, then you can think of a of a strong coupling of this macroscopic system with the cavity field. And if you convert the spin variables to the bosonic variables, and keep in mind that we are dealing with a macroscopic system, we have very large number of spins in the system. So in that case, the spin operators can be approximated by the bosonic operators. Then one would find that the effective coupling of this macroscopic system to the cavity field will go as square root of n, which is the non-total number of spins in the sample. And it is this factor, square root of n factor, which enabled experimentalists to observe the strong coupling. So here is the experimental result for the strong coupling of the cavity mode to the Kittel mode. And in the experiment done in Tokyo and in Yale, the effective coupling parameter was like 47 megahertz, and cavity damping and the magnon damping parameters were of the order of megahertz, and therefore one was in the strong coupling regime, and one sees these two clear polariton branches. So now I want to move on to the case of two samples in the cavity, and the effective coupling between these two, which is produced by the cavity. Now we know already from quantum optics that if we have two level atoms in this cavity, and if the cavity is far detuned from the frequency of these individual atoms, then there is a dispersive interaction between these two, which is produced by their common interaction with the cavity field. These two atoms are not interacting with each other, but they get effectively coupled to each other via the cavity mode. And this is the form of the effective interaction. And this is called the dispersive interaction. So these ideas have been taken over in the context of magnetic systems. So here you have two magnetic systems. One of them is pumped by a microwave field here. And because of this effective coupling in the cavity, you have a transfer of the excitation from this to this sphere. And this transfer takes place via the cavity, which itself is in the vacuum mode to start with. Now, these results so this is the linear regime. So these results can be generalized to the nonlinear regime if you drive this system with a strong microwave field. So what happens in that case? The nonlinearities of the system come into play, and the nonlinearities arise because there are internal magnetic fields in each of these spheres, and the internal magnetic field itself is proportional to the magnetization Because of that, one gets effectively a nonlinear interaction in each of these spheres. And the nonlinear interaction has this kind of a structure where U is the nonlinearity, and the magnitude of this nonlinearity depends on the size of the spheres and is of the order of few nanohertz. So now you can look at the nonlinear effects in this system. You apply a strong microwave field to this, and you look at the excitation of this sphere. And depending on the frequency of this driving field relative to the frequency of these individual spheres, you can get bistable behavior or the multi-stable behavior. So this is the magnetization produced in this sample as a function of the drive power and for different frequencies of the driving fields. And we had a collaboration with with huge group in Zhejiang University, and they observed this multi-stable behavior in such a scenario. Okay, so far I have discussed the strong coupling regime, but there is also important physics if you are not in the strong coupling regime. And these two regimes, in these two regimes, you can get what is called the level repulsion, so which is the strong coupling regime. Whereas there is another regime which was not studied so much because most of the people concentrated on the strong coupling regime, where you can have the level attraction, and which is the opposite of this regime. And recently there is a lot of interest in both level repulsion and the level attraction. If you look at the eigenvalue structure, so in case of repulsion, this is the structure of the eigenvalue. In case of attraction, this is the structure of the eigenvalue. So these are the real part of the eigenvalues, and these are the imaginary part of the eigenvalues. So strong coupling regime, this is sort of weak coupling regime. And if you look at the behavior of the magnetization, so if you go back to this system, you drive this one and you look at what's produced here, or you can drive the cavity. So, so left panel gives you results for the magnetization in one of the samples or in both the samples when the cavity is driven, strong coupling, and this is the case of weaker coupling. This is the case of level repulsion, and this is the case of level attraction. And what you see here, that there is no central peak, whereas in the weak coupling case, when you have the level attraction, you see the emergence of this central peak. And what is being changed here is the relative frequency difference between the two samples. So when the relative frequency difference is 0, so this is the level repulsion and this is the level attraction. So quite distinct behavior, and this disappearance of the central peak in the strong coupling regime is also connected to the existence of a dark magnetic polariton. Okay, so So now I move on to the application of another idea from quantum optics. And in quantum optics, the squeezing-like interactions play a very important role. And so now we can think of cavities with parametric interactions of this form and can study the effect of these parametric interactions on the transfer of excitation from one magnetic sample to the other magnetic sample. And in particular, what I want to demonstrate that there are regions where because of this term, you have significant amplification of this transfer of the spin current from one to the other. So in terms of Hamiltonian of this whole system, this is the extra term that we had, which is due to the parametric interaction. And let's assume first for the simplicity that this that the pump which is driving the nonlinearity in the cavity, which is responsible for this term, has a frequency which is half of the cavity frequency, so that all the tunings can become equal. Okay. Now let's first look at the parametric cavity by itself, and we know that the parametric cavity has regions of stability, and there are regions where the cavity becomes unstable, depending on the detuning parameter and this coupling parameter G. This was the coupling parameter G. Now the structure of this stability region changes when you put the two magnetic samples, and so in this case, now we study this enhancement factor, which is the ratio of the excitation transfer in a parametric cavity versus the excitation transfer when there is no parametric cavity. And this enhancement factor is plotted here as a function of delta and G. And from here you can see that how much enhancement one can generate. And so if you look at this blue curve here, for example, that shows the enhancement in a parametric cavity if you put this squeezing like nonlinearity in the cavity. There are other regions which are closer to the stability boundary, where the enhancement factor can be much higher. So this is the logarithm of the enhancement factor. But even if you work quite a bit away from the stability boundary, you can still get the significant enhancement factor. And this enhancement factor, a detailed analysis shows, is connected to the existence of a eigenstate of the system with an eigenvalue which has this characteristic property, that the imaginary part of the eigenvalue goes to 0 if you are if you start reaching close to the stability boundary. And so we have a parametrically induced coherence in the system, and which is the reason why we get the enhancement in the excitation transfer in a parametric cavity. And this can also be connected to the higher order transition pathways. If there is no parametric cavity, then we have just this pathway which shows that if you have excitation in one sample, via the coupling to the cavity, it gets transferred to the cavity, which in turn can get transferred to the second sample. But if you put the parametric interactions in the cavity, then as you can see from here, that the new transition pathway is open. For example, by now this parametric interaction can go to this, to this, to this, and to this. So many new transition pathways open, leading to this enhanced transfer of excitation. Okay, so now I like to discuss the waveguide mediated interactions. So you can think of two magnetic systems, or a cavity here and a magnetic system here, coupled to this one-dimensional waveguide. So it is coupled to the continuum modes of this one-dimensional waveguide. And you can do a master equation calculation and in fact show that the reduced density matrix equation for these two systems has this structure. And the important thing to note here is that the common coupling to this waveguide produces a dissipative coupling here and a coherent coupling here. And the dissipative and the coherent couplings, they depend on the distance between these two systems. In particular, if the distance between these two systems happens to be a multiple of n pi, then this part of the coupling disappears and one is left purely with a dissipative coupling. So this dissipative coupling results in what's known as the anti-PT symmetry. And incidentally, the PT symmetry has been has been at the center of a lot of work in optics in last 20 years. And in last few years, people have started discussing anti-PT symmetry. So what is anti-PT symmetry? If you have a Hamiltonian of the system, and if you subject this Hamiltonian to a time reverse operation and a parity operation, and if it changes sign, then this is called the anti-PT symmetry. If you look at effectively a 2x2 system, so this is the effective Hamiltonian which have these dissipative terms included, then the anti-PT symmetry gives you conditions on these damping parameters, and pure anti-PT symmetry would result if this coherent coupling is 0 and detunings have these properties. So no gain is required to have the anti-PT symmetry, and this is the structure of the eigenvalue, the real part of the eigenvalue and the imaginary part of the eigenvalue. These are the EPs. For anti-PT symmetric systems, EPs don't have any particular value. What's important for the anti-PT symmetric system is the existence of an eigenvalue whose imaginary part goes to 0 for certain values of the parameter. And the emergence of this 0 is related to the bound state in continuum. So therefore, these kind of dissipatively coupled systems produce bound states in continuum, and these bound states in continuum can be used for sensing application. So in one of the works, we considered the sensing of the nonlinearity. So this is a nonlinear system. And we found that if you work close to one of the VICs, which is allowed because of the dissipative coupling, then the sensing capability go like this. This is the small nonlinearity. And so dissipative coupling can be used to sense quite effectively the nonlinearities in the system. Okay, so I'm going to speed up now, and one of the applications that we considered is the possibility that dissipative coupling can lead to ultra-threshold bistability. So we compare two situations, dissipative coupling and the coherent coupling in the cavity, and we found that the threshold for the bistability for the two kind of couplings were related like this, which gives you that for the dissipative coupling, threshold can be a factor of 5 lower. And the Hood group in Manitoba, they carried out experiments to look at this, and in fact precisely reported in this paper this result. So this is the ratio of the threshold, and this is the detuning parameter. And if you look at on resonance, so this is the dissipative coupling, and this is the coherent coupling. And so this factor was roughly 5 as we predicted here. So another application of this would be the interconversion between the optical and the microwave field. So this the effective coupling here is quite small, but this coupling can be enhanced by using the waveguide related effective interactions. And okay, so in final 5 minutes or so, I'm going to discuss the quantized states of magnons. These we can produce by using the quantum state transfer. So one can consider a strong cavity magnon interaction in a cavity, but now we derive the cavity with the squeeze radiation. And the idea would be that we transfer the squeezing to the cavity first, and then the cavity will transfer the squeezing and the quantumness to the magnon system. And in this way, one can produce squeezed states of magnons, and one can produce quantum entanglement between magnons. There is a new class of problems where you can couple a qubit to the magnetic systems, and this is a superconducting qubit. And so if you excite this qubit, suppose you prepare the qubit in the excited state, then you can transfer the excitation of the qubit to this magnetic system via the common interaction with the cavity. So the dispersive limit, the effective interaction is going to have this form. So this is the spin-off operator for the qubit, and this is for the magnon system, and this is the quantum state transfer Hamiltonian. So single excitation will go to single excitation, and so for the magnetic system, you would have this W state. Okay, so the details can be found for this quantum state transfer in the magnetic system if you derive the cavity with a squeezed radiation, and basically we make use of this beam splitter transformation Hamiltonian. So same way quantum entanglement, so derive with this squeezed light, you produce the squeezing of the cavity mode, and cavity interacts with the two samples, you produce two mode squeezing and the entanglement between these two samples. And that's how the quantum entanglement looks like as a function of temperature if everything is on resonance. And you can also use nonlinearities to produce quantum entanglement. And it turns out that the scheme where we derive the cavity with the squeezed light works better. Okay. Well, we have also looked at the magnon, phonon, and photon interactions and how we can transfer squeezing and the other properties to the phonon systems. So, because the time is running out, let me conclude. So what I have shown you, the strong coupling of magnons and photons and producing polaritons, cavity-mediated interactions between the magnons, different regimes corresponding to the level attraction and level repulsion, the creation of the nonlinear polaritons, multi-stable behavior, the waveguide QET-related effects, dissipative coupling of magnons and TPT symmetry bound states in continuum, and trilinear interactions, interconvergence between microwave and optical fields, and the use of quantum state transfer for preparing quantum states of macroscopic systems. Thank you very much for your attention.
Well, thank you very much, Girish, for such a wonderful talk. It's almost like a review and so many new results. The talk is open for discussion now. Vitali?
Okay. Thank you, Girish, for very interesting discussion of this clean and quantum system. My question is about the bound state in the continuum you considered. In principle, do you consider the bound state of the continuum for the waveguide modes or for just this homogeneous magnon modes? Because bound state experience implies that you have to restrict your radiation channels and then make these waveguide modes lossless. How you get this in this system?
No, waveguide is open. It's a continuum of modes. And what we have basically assumed that the bound states occur when the magnetic systems are interacting only with the waveguide mode. There is no other decay channel for the magnon modes. It's just the coupling with the waveguide modes.
But then where you have continuous spectrum?
That is the continuous spectrum comes from the waveguide continuum. The coupling to the continuum of the waveguide modes produces an effective damping of the magnons and also the coupling between two magnons.
Okay, in that sense, you're basically talking about the decoupling of magnon subsystem from the radiation, so the waveguide modes and radiation losses. This is your physical meaning of the bound state.
That's right, because I'm looking at an effective 2x2 space consisting of these two magnon variables. And in this effective 2x2 space, one of the eigenvalues has an imaginary part which becomes 0.
Yes, I see now. This is just for this discrete quantum subsystem, not for the radiation modes. Okay, thank you.
Yeah.
Okay. Muzammal Shaukat.
Thank you very much for a very nice presentation. And I just was interested to ask you that one, the dissipative term, which basically plays the collective damping with respect to the two-level system. And can we not see the superradiance or subradiant phenomena here?
Well, we do see effects like that, but we are just discussing the problem of two magnons. And so actually in our papers, we do have a discussion, particularly in the paper that we have on this attractive and the repulsive coupling. In that paper, we do have a discussion.
Okay. Thank you.
Okay. Any other question? Let me see. In your last problem about quantum entanglement, I mean, you talk about W state and so on. Are they in a steady state or they are temporal?
You mean this one?
Yeah. Yeah.
Yeah, so basically, I mean, if you know, in a sense, suppose you keep on pumping the qubit in the excited state. So in that case, it would be steady state. If you excite the qubit and then just leave it, then it would be a temporal thing.
Okay, I see. Yeah. Okay.
So it depends on how you pump. And so actually, let me also add this. There is a very recent experiment just appeared about a month ago, where people prepared a coherent superposition of this qubit, and then they produced a coherent superposition of the ground state and this state. Which theoretically is obvious, but experimentally these things are quite challenging.
Okay, any other question? Okay, if not, then let's all thank Girish for such a nice talk. Actually, we should thank both plenary speakers for this session. Olga, do you have anything else to say?
Well, just to thank you for wonderful chairing of the session. And we have to meet again in about 30 minutes for the next session on the seminar 1.
Okay.
Thank you.
Okay, thank you.
Bye, everyone.
Bye.
Bye.
Olga, are you still there? Can I ask you a quick question?
Yes, please. Yes.
Are all the Zoom links the same? Does it matter whether I log in through my personal page at LPHYS or
Doesn't matter.
Doesn't matter? Equal rights, sharing and everything.
Yes.
Okay.
Yes.
Okay. Thank you.
Okay. Alёsh, did you discuss today what we discussed? Everything is okay, under control?
Yeah, it's under control.
Okay, good. Thank you.